In section 4.1, we introduced compound interest. That was only able to be compounded a finite number of times. In this section, we introduced compound interest that's compounded an infinite number of times. And this is going to be called continuously compounded interest. One area where this type of equation appears is during the study of how radioactive material decays. And we'll look at such a problem. Let's go ahead and derive the formula for continuously compounded interest. Again, this is going to come from looking at the compound interest formula, then allowing our n to approach infinity. Again, here we have our formula for compound interest. This is going to be given by p times 1 plus r divided by n times, raised to the n times t. Let's go ahead and let m be equal to n divided by r so that we can rewrite this into a more convenient notation. This is going to be equal to p times 1 plus 1 over m raised to the m times r times t. Rewriting this one time, this is going to be equal to p of 1 plus 1 over m, close parentheses, raised to the m, raised to the rt. Recall that by the definition of the natural number e, if we allow m to approach infinity, then the number inside this expression is going to approach e here. So if we let our interest compound infinitely, then we can replace this entire expression with just the number e. So the formula for continuously compounded interest is going to be given by the following. This is a of t is equal to our principal again times e raised to the rt. A of t will give us the amount after t years. P is the principal amount. R is going to be the interest rate per year. And t is the number of years. Let's look at this example by looking at an application to how radioactive substances decay. A radioactive substance decays in such a way that the amount of mass remaining after t days is given by the following equation. Where m of t is measured in kilograms. Go ahead and find the mass when t is equal to 0. And also find the mass after 15 days. So part A is really a warm-up. We want to find what our mass is at time 0. Plugging this into the equation, we can get 13e raised to the negative 0.0015 times 0. This is equal to 13e to the 0, which is equal to just 13. So at time 0, we have 13 kilograms. In part B, we want to see how much mass is remaining after 15 days. So we're going to evaluate our function at 15. this is equal to 13e raised to the negative 0.0015 times 15. Using a calculator in Mathematica, we see that this is going to be equal to 13 times 0.977751. This is an approximation. And this is equal to 12.7108 kilograms. So after 15 days, we still have most of our radioactive material. Now let's do a comparison between compound interest and compound interest that's been compounded continuously. This is example 4. Let's see which of the following rates and corresponding periods will provide a better investment. In our first compounding period, we'll be given 5 1/8% per year. And this is going to be compounded semi-annually. In part B, we'll be given 5% per year. And this is going to be compounded continuously. Let's go ahead and compute each of these. In part A, we'll be using just the compound interest formula. This is A of t is equal to our principal times 1 plus I divided by n raised to the nt. Again, we're given that our interest per year is going to be 5 1/8%. Let's write this as a decimal. This is 5.125%. Which is going to be equal to 0.05125. Now the number of times that this is going to be compounded per year is semi-annually, which means our n is going to be equal to 2. Plugging this into our compound interest equation, we're going to get p times 1 plus 0.05125 divided by 2 raised to the 2t. Simplifying this is equal to p of 2.05125 divided by 2 raised to the 2t, which is equal to p of 1.05190 raised to the t. Let's go ahead and see what we're going to get in part B. Part B, we're continuously compounding our interest, which means that our formula is going to be given by the p times e raised to the rt. In this case, our interest rate r was given to be 5% per year, which is equal to 0.05. Rewriting this, we'll get p e raised to the 0.05 times t. And this is approximately going to be equal to p times 1.05127 raised to the t. So comparing these two values, in part A, we got A of t is equal to p times 1.0519 raised to the t, and in part B, we just found that this is going to be A of t is equal to p times 1.05127 raised to the t. So in this case, it's actually better to go with the less number of periods compounded, but the higher interest rate. And part A is the better deal because we're still dealing with an exponential, and the base of this exponential is higher than the base in part B. So letter A is the better offer.